Hello and a very warm welcome back to Travis Labs on this, the first Sunday after Epiphany. Friend and fellow Moosehead Peter has raised the issue that basically microwaves, he says, are better than induction hobs, and that he reckons that I could boil an amount of water in about a third the time it takes on a hob. So basically he's stating a microwave should be a lot quicker. Anyway, we're going to try that. We're going to have a straightforward race between the microwave, the Sputnik, and the induction hob. And we're going to see what gets there first. Then after that, I've got a clever little device that measures power consumption. So we'll take a measurement as to what uses more power and do a few little calculations. And we'll see what's best, microwave or induction hob. So let battle commence. So first of all, let's measure out some water. So I think about 200 mils should do very nicely. 200 mils of cold water that some of them going to put into each of these vessels. So okay, it is cold water. Both taps on here are cold water. It's the chalet, so I'm afraid I don't have any plumbed hot water. I'm just going to put 200 mils in there. That is 200 mils, or near enough. And let's put that in our tin, which we're going to put on the induction hob. And then let's put 200 mils into this glass. And that is 200 mils. So obviously we're going to put the glass in the microwave and the tin on the hob. Then we're going to have a race. So a glass in the Sputnik, 200 mils, a tin on the hob. And I really haven't tried this before, so I don't know what's going to be first. So yeah, the question is to start them both at exactly the same time. Well, let's see what I can do. So I'll set everything up. Let's get that up to, shall we say, well, we'll just keep going till it boils. So I set this for 5 minutes. Should be plenty of time. God, it's going to be a boring video if it takes 7 minutes. Anyway, I mean, yeah, it's going to be boring anyway, folks. But, you know, I mean, it's boring and really boring. Vern's going to say this is, you know, a 7 minute too long video. Because he's like that. It's fairly cruel. Okay, let's get that on. And so, right, and no matter which way I do it, someone's going to have a slight advantage. So what did Peter say? Okay, we'll give the microwave a slight advantage. 7 minutes. And go. That's going. Let's get this going. So we're on the small hob and I'm going to crank that up all the way. Whoa, it's moving. That's because of a bit of expansion underneath the tin, between the tin and the hob. Oh, I've turned my espresso machine on inadvertently. I'll do my electricity bill in. So there we go. Okay, so we're off. And straight race. And we can see how much time they've had from the microwave timer. So again, starting off with cold water, which has just come in from underground straight out the water main, so it's pretty cold. And so yeah, we're doing, so I've had a minute now, and no sign of anything yet. Do I keep you, you know, hanging on while this boils? As we know it's going to boil, but it's a race, so it's exciting. Hey, okay, it's going to be good. Vern, this is going to be a good video. Okay, it's not going to, you're not going to regret watching this. I mean, you can probably do something more constructive, but what could be more constructive than one of these Sputnik moments, eh? Let's face it, you're only going to be drinking beer or some cheap French wine. No sign. Oh, hang on. Well, a bit of vibrations, a bit of movement, but you know, no boiling. Bit of steam. Back to the Sputnik, and there is no boiling there either. Slight movement again, and yeah, a few bubbles forming. Not far off, I think, either way. So it's pretty much neck and neck. There is some movement. I'm sorry you can't see it too well through the protective grating there, but we've got some movement also. A bit of nucleation of bubbles there, and we've got a bit of bubbling, and we've got a bit of bubbling. My goodness, we've got a few bubbles rising, but we've got a full-on bubble here. Yeah, we got full-on boiling after it's 2 minutes 55 seconds, and oh dear, the induction is lagging behind a bit. So 2 minutes 55 seconds for 200 ml water in the microwave, and we've now got, it's just coming up to a full boil now, and there we have a full boil. So that is, yep, that's going to be what, 3 minutes and 20 seconds. Okay, so let's stop that. Make a note of those results. Okay, so we saw that microwave a bit faster, but remember the hob was on the lowest, you know, in a small vessel, a tin, on the small hob. What I think would be more fair, and I'm not going to subject you to the whole bloody thing again, but let's just do 200 ml in this saucepan, gives more induction contact area. So I'm just going to put again 200 ml, that's 200 ml into the saucepan, and see how long that takes. But I think, to be fair, that's okay. That glass is very hot. I'm using another glass, and I know, let's use the West Berkshire beer glass. The West Berkshire Brewery, what a nice design, beer glass. Tell you what, let's set it to 10 minutes. It makes it easier to calculate, you know, because I'm of the generation of pocket calculators. I'm a bit slow when it comes to calculating, so it's easy to see how many minutes it's had. Then we're going to have a look at the power that they're rated at, and then we're going to do a few more measurements. So then this one could go on and on. That's off, and this is now buzzing away now, and that's a bigger induction hob. We know for well that not much is going to happen for the first 2 minutes and 30 seconds. So I'm not going to subject you to that. So here we go. And we're coming up now to 2 minutes. And there's no bubbles forming yet in the West Berkshire Brewery beer glass. But, oh my goodness, and we're starting to get quite a lot of bubbles. And really, that is taking off now. So the induction hob then is pipping the microwave to the post. So we've got boiling. We've got full boiling, and that is really under 2.5 minutes. So 2 minutes 20 seconds, and we've got a slight nucleation now in the beer glass, but really 2 minutes 20 seconds, and that is now boiling flat out. You can see there, whereas our beer glass has scarcely started to bubble, and we're coming up to 3 minutes now, and of course we expect to see some action round about now. 3 minutes, and there we go. We have some boiling now at yeah, just approaching 3 minutes. That's 2 again as before. We've got full boiling now at 2 minutes and 55 seconds. Now let's take a look at some power outputs. I'm looking at the specs. The bloody thing's upside down. I'll turn the phone upside down so we can see now the induction heater is rated at 3000 watts. You know, we're just using one of the hot plates, and of course that doesn't allow for any inefficiencies. So let's take a look at the microwave, and I've got a max 1200 watts going in and 700 watts coming out to actually heat. Obviously there will be losses in the induction hob as well. So I bet you haven't seen one of these before. This is a plug-in power and energy monitor. It's got various buttons here. Look, I can measure volts, amps, watts, hertz and kilowatt hours. So okay, let's plug that in and have a look. So I'm unplugging the microwave. Let's see. That plug's going to get in the way, but I don't care. So that's now. So what's that? Volts. Yeah, it's fascinating. 241 volts. Obviously, it's not going to give any amps or watts. It's not plugged into any hertz. 50 hertz. Right. So let's plug the microwave into that and do a little measurement, shall we? So this time I'm going to measure how many kilowatt hours it takes, or how many watt hours it takes to boil 200 ml of water. First of all, using a microwave, then using a hob. Then we'll compare the two, work out how many joules they've used, etc. And we can have a definitive answer as to what's best. Anyway, so I'm going to use a Loddon brewery beer glass for this experiment. Loddon, craft brewery in Oxfordshire actually, but just outside of Reading. So it's 200 ml. That's bang on the mark there, and that's going to go into the craft beer glass. That's going to go into the Sputnik. Let's set that to record. Okay, well it's accurate to, well, 10 watt hours, I suppose. Anyway, that should give at least a reasonable measurement of our energy consumption. So let's just set this going until it's until it's boiled. So let's put it. We know it takes about 3 minutes, so let's put 4 minutes onto that to give it some contingency. And I'm going to set that going, and let's follow this meter. So we've got no consumption at all at the moment, no measured consumption, obviously, and let's just see how this takes off. So this is quite exciting stuff. Now, Vern, I hope you're still being attentive. Hey, this video is going to be one of my longest yet. Just think what I've saved you in Dordogne wines. You probably knocked back about 4 glasses by the time I finished this video, and I've saved you that. Perhaps you can save them for me when I come and visit you in the Dordogne. Sorry, I've got to keep some kind of inane banter going while this boils. So the Sputnik's off. I'm sorry, nice to see the Sputnik in its full glory. So I'm gonna, put out the light. I'll probably trip over something. I can't see the consumption. Sorry, that's the whole point. Let's put this light on. Consumption is now 0.02 kilowatt hours have been consumed. Okay, so that's all happening, isn't it? It'd be nice to see it actually go to 3 before the bloody thing boils. So anyway, we're going to get a rough idea. I suppose it's not going to be that precise, is it? But 3, there we go. It's gone to 3, and we're coming up to coming up to 2 minutes. It'll boil in about another 45 seconds. So there we go. Yeah, and it's going to boil, and that's at 0.3, that's 30 watt hours. Not boiling yet. So yeah, what did I start at? 4 minutes. So 2.5 minutes in. So it's going to boil in a bit, isn't it? Slight movement, slight nucleation occurring there in that craft beer glass, and we're getting there. It's starting to bubble. It's starting to bubble again. Yeah, it's starting to bubble as we approach 2 minutes 50 seconds again. So let's turn that off. So I'm going to stop that. Stop. That's stopped. Okay, that's stopped. And our consumption. Okay, well, I'm just for the purposes, let's hope we don't get a tie, because obviously it's, you know, accurate to one decimal place. So it's not brilliant, but we got 0.04 kilowatt hours, so 40 watt hours to boil 200 ml of water in the Sputnik. Right, let's see what the induction hob can do. Let's be completely fair. This is the saucepan I used. It's still warm. Let's not give it any advantage. So I'm going to take another saucepan which is cold, a bit smaller. So it might take a bit longer, but that's not the object anyway. The object is to find out the energy consumed. So yeah, I'm going to be totally fair. I'm taking a cold saucepan. I mean, the craft beer glass I used was cold, so you know, fair's fair. And I'm going to stick, there we go again. That's on the mark. 200 ml there into a fresh saucepan. So there's a bit of a faff because of all the cables going behind here. But anyway, I've got my 8 kilowatt block here. That's the one for the induction hob. So let's okay, this zeros, it is zero whenever you unplug it. So I'm putting this in here. As you can see, it's zeroed itself. We've got our voltage by default output on the display, and plug the hob in. And let's switch that to, okay, record. Right, let's get going. 7, 8, 9. So full whack. And here we go. And consumption. Okay, currently at 0. So yeah, well, it's going to heat up, isn't it? So that is 10 watt hours appearing on it, doesn't. And point 2, it's using quite a lot of energy. I think that's going faster than the microwave. That wheel on the meter will be whirring around a bit faster, because I think we're using energy a bit more rapidly here. That went up to point 2, didn't it? Fairly rapid. Let's hope we get a rapid boil. And we are getting a few bubbles forming. So we've got 0.4 to bead. I do hope it's not a tie. Come on. So we've got a few bubbles. Some boiling. 0.3, still 0.3. Still 0.3. Still 0.3. And we've got, so that's boiling. Boiling at 0.3. Come on. You can't deny that is that's boiling, okay? So it's going to go to 0.4, obviously it's still in. And so it was boiling at 0.3, you saw that, okay? So it's time for a few back of the envelope calculations. So the Sputnik, okay, that used 0.04 kilowatt hours, so that is 40 watt hours. Induction, and that was 30 watt hours. It's kilowatt hour is 1,000 watts, 1,000 joules a second, isn't it, for an hour? So that's that many joules. No? Am I right? 40 joules. So it's 40 times 3,600 number of seconds in an hour times 40 gives the total consumption in joules. Obviously that's 30, same thing. So there are my calculations. 40 watt hours total consumption measured by our eco device. So that's yeah, 40 joules per second by the number of seconds in an hour, because it was a 40 watt hours is what it used, or 0.04 kilowatt hours, which is that. Anyway, according to my arithmetic, that's 144 kilojoules, and of course we do the same calculation for the 30 watt hours from the induction, so it's 108 kilojoules. So 144 kilojoules was used by the microwave to heat up 200 ml of water, and 108 kilojoules was used by the induction hob to heat up 200 milliliters of water Okay, let's do a few more calculations. Bloody hell, that's great, isn't it? So the thermometer's no bloody good. It starts at 100 degrees. That's for me jam. A lot of jam up here. It's nice. Made from Scotch bonnets. Okay. Anyway, sorry. That's no good then. That thermometer's no good for measuring room temp. I've got some water straight out the tap. It's it. Here we go. Perhaps I could do humidity and temperature. How about this? This is German made. It's got to be good, hasn't it? I don't know. Maybe. What do you reckon? I'm going to bollocks it up. It's worth it for the cause of science. Humidity will be registering 100%. And see if I can get something worth reading. Yeah, I'm going to leave this a few minutes and see if it does actually like go down and stabilise at anything. Right, that's got to be it. So I've stuffed up my hygrometer, but the thermometer type. Yeah, more just move round, please. Anyway, I actually changed the water. It took so long. I thought the the tap water was equilibrating with the room temperature, so I changed tap water. I don't like it. I don't think this is really like 18 degrees, this water. I don't like it, but I'll have to go along with it. I think it's a bit colder than that. Who knows? It'll just come out of the ground, doesn't it? It's going to be colder. But I don't know. I haven't got a better way of measuring it. So I'm going to take that. I mean, look, that's still got to go down a bit. Let's call it 15, shall we? Is that okay? I mean, it's quite cold to the touch. I need a thermometer. Perhaps I should get sponsorship, and then I could buy one off eBay or something. Can't be very much. Anyway, so we'll call that 15 degrees. And right, let's now get over to do some calculations. Of course, anyone who's done a, GCSE or CSE chemistry will be intimately familiar with the Stark and Wallace. So back in the days before the internet was even thought up, people were using these Stark and Wallace. And I'm just looking at this. What heck should I be looking at? So thermodynamic data seems like a good place to start. And so we've got the, oh goodness, this C underground sign, P, donates the standard molar heat capacity of a substance at whatever, 25 degrees centigrade room temperature. So that, what the heck does that mean? Well, let me think. I can remember. You said looking at Google. So the molar heat capacity is the amount of energy required to raise the temperature of 1 mole of a substance by 1 degree, and the units in the SI system are joules per mole. So all I've got to do is find water, H2O. Blimey, what a lot of heat capacities we've got. So we've got water. Why are there 2 H2Os? Oh, I see. State. Yeah, obviously one's one's would be liquid, won't it? So liquid. And that last thing is it's H2O2. Oh, I won't be. No, hang on. Okay, no one's measured it for H2O2. I wonder why that is. So right, we've got a 75.3 H2O per degree to move it through 1 degree. Okay, a mole, Avogadro's number. Okay, so a mole of water is its molecular weight in grams. Molecular weight of oxygen is oxygen. Yes, of course. It's 16, isn't it? Yes, we all know that. 16. molecular weight of hydrogen obviously is 1, 2, hydrogen, H2O, that's H2O is going to be 18 grams per mole of water. So it's 200 mils, 200 grams. If I divide 200 by 18, I get the number of moles. It's 11.1 recurring moles of water. Okay, this is getting interesting. Getting close to a conclusion now. Okay, Vern, don't lose patience. Right, so we've got 11 moles. Now, I heated it, well, we went with 15 degrees for our water temperature. So we heated it up to boiling point. And we're just looking at raising that then through 85 degrees, from 15 degrees to boiling point. So according to my calculations, we've got this constant here, our thermodynamic data from our Stark and Wallace, which states that it takes 75 joules per mole of water to push it up 1 degree. So 75 joules per degree. So that is, how do I got a point there? 75 times 85 times 11. Are we okay with that? Sorry, that's 85. No bloody point. 85. Let's do that properly. So, okay. 73 joules and 11 moles going through 85 degrees. Wow, it's simple calculation, simple multiplication. Okay, so let's do that. Result is 68,944 joules is what it takes to heat that much water, 200 mils from 15 degrees to boiling point. Now, obviously, there's going to be losses here. So, you know, I was only looking at the water boiling. I didn't have a thermometer in, and I didn't stop the moment it reached 100 degrees. So it's chewing up a lot of energy undergoing that phase change. So taking the water, making it to water vapor takes a lot of energy, a heck of a lot of energy. And I'm only, you know, stopping the clock, so to speak, once I've seen that phase change occurring. That's going to be gobbling up energy. Really, I should have just done it with a thermometer and just measure the temperature difference, and preferably not all the way to boiling point, because I'm using up energy to make the water vapor out of the water. So, you know, I'm being unfair on these devices. Their efficiency is dropping just simply because of the way I'm doing the observations. It's not really fair. But basically, we've got this figure of 60, well, we call it, you know, 70, 69, call it 70 kilojoules is the kind of energy that I should be putting in there if the device was 100% efficient. I'm out of envelopes, so we'll have to use this container, which is from the station grill, and a chicken curry, and it wasn't a very hot one though. So we're happy with that, are we? 70 kilojoules is what it takes to heat 200 mils of water at standard, well, no, it doesn't make any difference. 200 mils of water from 15 degrees to 100 degrees at 100% efficiency. Okay, how does that match up with our devices? So off our envelope, we've got these figures. Sorry, I don't know why I bothered working it out per litre. Anyway, we've got the figures for heating 200 mils of water. Right. So there we go. And I've just transferred them over to this new medium here. So the Sputnik used 144 kilojoules to heat up that 200 mil. The Induction used about 108. Obviously used a bit less. And there you have it. So our efficiency, Sputnik used 144. So I'm dividing 70, which is our ideal at 100% efficiency. It would take 70 kilojoules to raise 200 millimeter water from 15 to 100 degrees. Sputnik does it in 144. Sputnik does it in 144 kilojoules. So 70 divided by 144 gives 49% efficiency for the Sputnik. Again, unfair because I was already watching it boiling. So, you know, some energy had been absorbed into making that phase change, whereas, you know, I'm just want to get the efficiency for heating to 100 degrees without actually boiling. As I was, you know, observing boiling, to give myself indication, you know, some energy was being expended. But we've got a figure of 49%. Anyway, this is relative, but so 49% efficiency for the Sputnik microwave. Right, let's see how our Lincat professional induction stove lines up with that. And there you have it. So we used 108 kilojoules to heat up that 200 mil from 15 degrees to 100 degrees. Ideally, that would have been 100% efficient system. That gives the induction hob 65% efficiency versus 49% efficiency. So with that, the induction hob, well, it's slower if you heat it in a tiny little tin, but if you heat it in a saucepan, it's quicker and also it's more efficient. Let's just see what the internet says about that kind of result, since really I haven't checked this, I promise, yet at all. Here's a bit on the web. So I just typed in what's the most efficient way. Anyway, someone's done all this. Let's have a look, see what it says. You know, obviously it's probably most efficient to stick an element in, but anyway. So there we all look at that. They've done all this nonsense. I needn't have bothered, eh? Just look it up and saved yourself all this time looking on YouTube, Vern. So it says here, a microwave is about 50% efficient. Stovetop 70. Well, yeah, but it takes ages on a stovetop. Electric tea kettle, yeah, it goes straight in, doesn't the elements completely surrounded by water. An induction stove. An induction stove is 85% efficient. More than a bloody kettle. Isn't that amazing? Isn't that amazing? So it goes straight, energy goes straight into the base of that saucepan, straight into the water. 85% efficient. I was letting that boil a bit, so that was a bit of phase change. A lot of energy went into that. Accounts for the 15% versus 49%. So I was pretty much bang on with the microwave. So there we go. We thought we'd do it the interesting way. We didn't use the internet once to work this out, and we got there using Stark & Wallace, an induction hob, and a Sputnik. So that's it from Travis Labs. I hope you've enjoyed the show. If I think of anything else very interesting, I'll make a video and make Vern get really bored. Anyway, Peter, you were on about microwaves being faster, better. No, they're not. There we go. Till next time. See ya. Goodbye.